You ever wonder what really makes one app feel lightning fast while another one just, well, chugs along? It's a great question, and the answer goes way deeper than just the computer it's running on. So let's get into it and figure out what developers really mean when they talk about fast code. Okay, so you'd think the easiest way to measure speed is to just time it, right? Pull out a stopwatch and see how long it takes. But here's the catch. What happens if you run that same code on a brand new supercomputer versus, say, a 10-year-old laptop? Obviously, the times are going to be completely different, but the code itself hasn't changed one bit. So yeah, a stopwatch just doesn't tell us the whole story. We need a much better measuring stick. And that's where this really cool idea called time complexity comes in. This isn't about seconds or minutes. Nope. This is the expert's measuring stick. It's the professional standard for figuring out how efficient a piece of code or an algorithm truly is, no matter what machine it's running on. Now, if you look it up in a textbook, you'll get a formal definition, like this one. Time complexity is the amount of computational time an algorithm needs to finish its execution. And that's true. It basically gives developers a universal language to talk about performance without getting bogged down by the hardware. But let's put that in plain English. Really, a simpler way to think about it is this. Time complexity is all about predicting how a piece of code is going to behave when we throw more and more data at it. Is it going to stay fast and zippy, or is it going to slow to a crawl when the job gets bigger? That's the real question it helps us answer. So, if we're not using a clock, what are we using? Well, the secret is surprisingly simple. We count. That's it. But we're not counting seconds, we're counting something way more fundamental to the code itself. The whole idea boils down to this. We find the most important action, the main operation in the code, and we just count how many times it has to run to get the job done. Just like the quote says, it's quantified by that count. This number, not seconds, is what really tells us how good our algorithm is. So how do we actually do this? It's really just a simple 3-step process. First, you pinpoint the core operation. The main piece of work being done. Second, you count how many times that action happens. And third, and this is the most important part, you figure out how that count changes depending on the size of your input, which we usually just call n.
Program 1, we're looking at the first structure you provided, and it's the very definition of linear efficiency.
It is. If you visualize it, Program 1 is designed to be the simplest possible case. You see a single loop. That loop is iterating from a starting point 0. Up to n-1.
Where n is just the size of whatever list or array you fed it.
And the structure itself it immediately tells the story, doesn't it?
It does. The total number of steps the computer takes depends directly, 1-to-1, on the size of the input, n. If you give it 100 items, it takes about 100 steps.
Double the input to 200 items.
The time taken roughly doubles. It's a proportional relationship.
And what I found fascinating in the analysis was the focus on the constant time operation inside that loop. Here, it's just simple addition and assignment.
Right, a very fast operation.
It doesn't matter if n is 10 or 10 million. That little operation itself is basically instantaneous. The cost driver is purely how many times you repeat it.
And that's the core of the ON derivation. The loop executes n times, and since everything inside is a fixed constant amount of time, what we call O1, the total time is just directly proportional to n.
You drop the constant factors and you're left with ON.
Exactly. Program 2, the one dealing with matrix addition, that gives us the classic blueprint for quadratic time. And the structural detail is just it's non-negotiable nesting.
Let's just visualize the execution for a second. The math is simple, but the performance implications are huge. You have the outer loop running climb times.
Right.
But for each of those n times, the inner loop also executes its entire course, which is also n times.
Think of it less like reading a list and more like filling out a giant grid or a spreadsheet.
Okay.
If your spreadsheet is n rows by n columns, to touch every single cell, you have to perform n times n operations.
In this matrix addition example, the little operation inside the core is element by element addition, which is O1. But because that tiny step is encased in this n by n structure, the total operation count is n squared.
So program 3 starts by initializing 2 separate integers, a and b, and then it runs 2 completely separate independent loops, one after the other.
Let's break it down. We have loop 1, which runs for n iterations. It's adding a random number to variable a. Since this loop only depends on the input size n, its time cost is on.
And then after that's all done, loop 2 starts. It runs for m iterations, doing a similar thing to variable b. So its cost is om. Because these operations are independent and sequential, we just add their complexities. The total time is the time of the first process plus the time of the second process.
So ON plus OM,
Yeah.
which gives us ON plus M.
Exactly.
And the structural contrast with ON plus M.
Exactly.
And the structural contrast with ON is M immense. If N and M are both, say, 1,000, this sequential process takes 2,000 steps,
But if they were nested,
1,000,000 steps. So sequence adds, nesting multiplies.